for some of the homework problem you have 1.3,
Yeah.
we're asking you to create a differential equation
Yes.
for like falling bodies and stuff
Yeah,
like that.
yeah. I gave you some examples. I can't obviously in the class cover everything. In fact, maybe I should go over that one because a lot of people did very poorly on that one. That was one with the spring. Let me do that one. It's great you brought that up. I mean, the ones which I assigned, where I thought were things that you had in, pretty much in your physics courses. And let me tell you what people kind of screwed up on this one. I think this was one, tell me if I'm wrong, it was like a spring mass system, right?
Yeah.
The first thing they did is they showed, here we are in the undeflected position, okay? So that's no load, okay? We're assuming that the spring has no mass to it, okay? So the way you would realize that if the thing was attached, you just hold it up so the spring doesn't stretch at all, right? Okay. Then they showed you another diagram over there where the thing was loaded, okay, and it was stretched. So let's do everything relative to this diagram. Okay, starts here. Now it's stretched somewhat. I'll exaggerate it a little bit, okay? And then here's the mass M, right, or weight energy, right? And this is basically static equilibrium. That's what the problem had stated, okay? And I think what they did is let's just draw a line over here, okay? And we'll call this distance that it went down S, okay? Static equilibrium, okay? You make a free body diagram of this. I don't think you have to do that, right? Remember, there's a spring there with the modulus K. The force is K in words. The restoring force is K times the stretch, okay? Here it's zero stretch, okay? It's an equilibrium, okay? So when you do the equilibrium over here, what happens is you find mg has to balance the force of the spring, which is K times S, okay? So it allows you to solve for the static deflection in terms of the mass, gravity, and the spring constant, or S equals mg over K. That's the static deflection. It's just sitting there, not vibrating, okay? And it makes sense. Certainly the stretch is proportional to the weight. And yeah, the stiffer the spring is, the less it's going to stretch, okay? Then what they do, here's a third one. It's nice how they drew them all together, okay? Now what we're going to do is have the thing actually vibrate. I think they used Y for that. So we'll bring it down basically over here, okay? Okay, it's going to go past that position. I'm going to exaggerate it. And let's say now the mass is over here. These really should just be points. So now here's the mass, mg down there, okay? And let's go over here now and say that this displacement over here is y of t, okay? Now it's very important that S is a constant. S is not a function of time. S is the static deflection, right? Y of t, in words, is the deflection of the mass beyond the loaded equilibrium position. See? And the idea actually of this problem was to show that if you choose your coordinate y to be the deflection relative to the loaded equilibrium position, as opposed to the undeflected, the equation becomes what's called homogeneous. It's much simpler, okay? So what happened, a lot of people wrote things in, remember that F2 in there? I don't know where F2 came from, but you know.
The examples had
they had
equations
F2?
in
Okay,
it.
okay.
So,
Okay, so I was looking at it as F2, and I think, well, yeah, that was kind of strange. But you ever understand basically that this is the static deflection, right? And here's the loaded equilibrium position. Okay? No, sorry. Here's the static deflection, and here the thing is vibrating. And y of t is a deflection relative to the loaded equilibrium position. It's not the deflection y relative to this guy over here, right? You can see it from the diagram, right? Okay. Oh, I didn't draw my diagram well. Sorry. It's relative to the loaded equilibrium position, which is over here. Sorry, okay? This is your y. It's like a distance, okay? Yeah, I bring it relative to x. Okay. So now we're going to write Newton's law over here, right? And let's do positive down, okay? So we have basically the forces are what? mg, right? Down. And now there's a spring that's restoring it. So it's the spring obviously is in a state of tension, so it's going to bring it up in this case. Minus k. Now, if you're very careful, what's the formula for the restoring force of the spring? It's the modulus k times the total stretch relative to zero stretch, which would be y plus delta. Y plus s. That's critical. okay? And that, of course, is equal to m times the acceleration. Okay? So, if I bring all the, y double dot, right? Okay? The deflection is s plus y, but only y is a function of time, so we take the second derivative to get the acceleration. The derivative of s is 0, so it's y double dot. Okay. So we can write this equation in the form m times the second derivative of y with respect to time, right? Let's bring this plus ky. Okay, bring all that stuff together. And on the right, I'm just going to have mg minus ks. Okay? But look at the definition of s, right? Mg equals sk. Okay? So what happens in reality is that these two guys, mg and ks, basically cancel, and you have a 0, and then it looks like a nice homogeneous differential equation. Now, there's nothing wrong if you have basically let y be the deflection relative to the unstressed position, then the mg would appear there explicitly, and it would be non-homogeneous. And when we solve non-homogeneous equations, you'll see it's just a solution of the homogeneous plus that amount, okay, which is a perfect agreement to physics over here, right? Okay? So that's basically the proper way to do it. Okay? A lot of people didn't do that. You know, they got to this equation and somehow they knew what the answer was and they just canceled mg. What I was looking for is that you realized that s was mg over k. Okay? So, okay, again, on an exam I would never give you something that would depend upon some physics or something. You know, it's going to be basically solve this equation, that type of thing. Okay? But I thought it would be interesting to look at some problems that, you know, of that nature. Okay, so with no further ado, let's go on to today's topic, which will be direction fields. This is a qualitative way of solving differential equations. And it works basically for any equation of the form dy dx equals f of x1. Okay? And that's basically pretty much your most general first order linear differential. First order nonlinear equation. It could be linear, right? But dy dx f of xy, where f is any arbitrary function of x and y, in general is a nonlinear equation. And like I said, nonlinear equations are rather difficult in practice to solve analytically. Some you can, and we will do some of those. But in general, it's, you know, you have to use, you know, some numerical method or some graphical technique. This thing called direction fields is a graphical technique, and I'll describe it, okay? And just as an example, let's do the following, okay? Let me do dy dx equals, let's see the problems I'm doing here, 0.2xy. This is the one that's done in the book. 0.2 2/10, I guess. 0.2x1. Okay. Now, you recall from calculus that dy dx is what? It's just the slope to the curve at a certain point. So, if indeed, okay, let's just plot this in the xy plane over here. Okay, here's x and here's y. And what I say for this will apply to this in general, obviously, right? Suppose now you give me a certain xy pair, I can then calculate numerically the right-hand side, right? And find out what the slope at that point is, okay? So for example, if I go to the point x equals 1, y equals 1, the slope is 0.2. So I draw a small line, say 0.2 as a slope, or 0.2 look as a small slope, something like this. Here's 1, 1, right? 1, 1. I have a slope of about 0.2. Okay, not a good diagram. And therefore, we know that the curve in the vicinity of that point, the solution curve basically looks something like that. It has a slope over there, okay? And we're assuming over here that a solution exists, okay? And indeed, you can use the theorem that we had. 0.2xy is what? It's continuous everywhere it's possible. Y is continuous, and therefore, through any point there exists what's called an integral curve, okay? Curves which satisfy the equation, the differential equation called integral curves, okay? Then what can I do? I can then move, say, maybe to this point over here. Go to x equals 1.1, y equals another value, and then I'll get a curve that may be a line like that, okay? And the idea of this direction field is to basically do this thing for the entire xy plane, okay? You go to different points over here in the xy plane, and you just calculate the slope. Perfect for a computer, okay? Terrible for a person to do, right? Drew a little line here. These are called lineal elements. What they are, they're kind of tangent lines to the solution curve at a point. They're approximations very locally to the curve. Okay? So let's do as much as we can though, just without the computer, to get an idea what goes on, okay? So here we are on the XY plane, okay? Okay, one of the things that you want to, wish I could just draw the axis straight. Good, okay? One of the things that you want to do basically is see where's the slope equal to 0? Well, the slope will equal to 0 when x equals 0 or y equals 0, okay? So for example, over here, you're always going to have like a 0 slope. I should those in red maybe, okay? Over here, you can have a 0 slope. Over here, 0 slope. Over here, everywhere along here, a 0 slope. So I'm just going to draw that, okay? We also get a 0 slope. That's when x is equal to 0. You also get a 0 slope when y is equal to 0. Everywhere along here, right? 0 slope. So the curves, right? They all go tangent like this. Okay. Suppose I'm at the point like in the first quadrant. Like x equals 1, y equals 1. We know the slope is 0.2, and it increases with x and y, right? So therefore, maybe it'll do something like this, right? And then we come over here, we're going to have a 0 slope over here. What happens when we go to the left over here? In that case, y will be positive, x will be negative, we have a negative slope, and again, something may be like this. It increases, the absolute value of the slope increases as we go more and more that way. Suppose we're in this quadrant over here. X is positive, y is negative, it's going to be a negative slope, it's going to fall, right? Something like this. And over here, it'll go like that. Now, of course, I just drew one curve, but there'll be a family of curves like this, and like this, etc., right? And what we're going to look at is a piece of software, okay, which I wrote. Okay, we'll go over it first. And what it will do, it won't draw these curves in black that I've shown. It'll draw all those little red arrows. There'll be a little arrow, and what you do is just tell MATLAB, go to this point. It takes the XY plane, breaks it up to a grid, okay? Now, you have to decide the range. You can go from x equals -2 to +2, or -3 to 3, or -80 to +80. You have to kind of play with that, and also the y range. So you'll see the program takes an x range, y range, okay? It'll then calculate, for this problem, the slope at a point, and we'll tell MATLAB to draw a little arrow at that point, okay, pointing in the direction of the slope. And you'll see a whole XY grid with a whole bunch of these arrows. And then if you kind of draw the arrows, if you draw the arrows kind of visually, you get an idea of the flow field, so to speak, or the solution curves that go through different points in the XY plane. Now, what puts us on a specific solution curve? An initial condition. We know that, right? Here I just have a program that doesn't have any initial condition. It just says, give me the direction field for dy dx equals 0.2xy. So it'll be all over the place. But once we choose a particular initial point, maybe like I said, you know, it has to go through the point x equals 0, y equals 5, then, you know, we'll have this one, and then you would see only that curve, okay? So we'll do stuff like that, okay? But this idea here of the direction field is to just look at what the curves look like without regard to the initial condition. So you get a feel of the nature of the curves. Are they increasing, decreasing? You know, what do they look like qualitatively? Okay. So let's get the thing fired up over here, okay? And as I go through this, we'll go through it for this, I have it coded for this specific problem, and then I'm going to indicate to you how you alter that program that I wrote in order to do the homework problems. By the way, this script will be found on the Moodle page. There's a folder at the top, I believe it's called MATLAB Scripts, and this one is called dir.m, I think, for direction field, something like that, okay? So. Okay. Let's see. Hopefully this will work. Okay, there we go. Okay, so the name of the file is it's dir_field.f. That's the end file. Okay, and of course to execute it's a script. It's not a function. So you basically you can look at the I forget what it's called, some window over there. Remember how I did run? Or if you're on a Unix workstation, just type in the directory dir_field and it'll execute. You know how to execute a script. We went over that. Okay. So template for producing direction fields in MATLAB, okay? And I even tell you section 2.1, example 1 in the text, ydx equals 0.2xy. Okay. Okay. First thing you have to do is, like I said, you have to take a range. You know, I want to look at the slope over a grid in the xy plane. How far do you want to go? Okay? So in this particular problem, I made the x range go from -5 to +5 steps and a half. Okay? And I did the y range the same thing, -5 to +5 steps and a half. Okay. Then we got this crazy mesh grid thing. Okay? Okay, so that's just basically, you know, that's just there. Now, let's just, you know, we'll talk later how we alter it, okay? This thing, don't touch that, okay? And like I said, what it will do basically, it'll take that x range and y range, and it'll give you matrices x and y. That's the way MATLAB operates, okay? So that every point, basically, you have kind of duplication there. If you look at this X matrix, it had duplicate columns. This Y matrix had duplicate rows. Okay? Okay. Now, before I go on, the new function over here, which is built into MATLAB, is called Quiver. Okay? Quiver was made to do things like in fluid mechanics. Okay? Where you have like a velocity field, right? Suppose I'm looking, maybe want to model the flow with some type of duct like this, right? And the velocity field maybe goes like this. Over here maybe goes like that, right? The velocity is a function of x and y over here, right? So what the quiver will do is, look at quiver, how many arguments? That's x, y, okay? So normally the way you use quiver is you do quiver, okay? The x and the y, remember that's the range basically. And notice when I do quiver, the x, y is that crazy thing from mesh grid, okay? But essentially, just think of x and y basically as telling you where